Hello everyone! In this video we're going to look at another special case in linear programming, and much like the other videos in this series, I'm not going to take the time to necessarily explain every single part of the question. If you have any issues at all with the formulation of the mathematical model, of being able to graph that model, of being able to find the feasible region, and from there find the optimal solution, please consult prior videos that are available in our Fanch Online course site. If you would like to try to solve this problem on your own and find out where the special case comes about, please pause the video now, and once you've identified it or need a little help finding where it is, restart the video. But now I'm going to jump right into the question and go through as far as I can until we see something come up that we haven't seen previously. Beginning with the formulation of our objective function, here we are dealing with a maximum profit example. So as always, we either start with the words max or min. Here we want to make sure that we point out that this is a maximization problem, followed by the mathematical formula that will allow me to solve for the maximum profit, which is 15m plus 10c. And again, here, I pointed this out in a previous video as well. We really have to be careful with units, because here I see some of the information is given to me in minutes, and some of the information is given to me in hours. So as was pointed out in that previous video, within an individual constraint or within the individual objective function, as long as I stay consistent within the units within that constraint or that objective function, I will be okay. I can have different units in constraint 1 than I have in constraint 2. That's not a problem. But what I cannot have is different units contained within constraint 1 or different units contained within constraint 2. So notice that here, when I'm talking about 15m and 10c, well, those are different units, and we're seeing up here, we're talking about minutes. These are dollars. So there's no issue with having dollars in one constraint, minutes in one constraint, hours in another constraint. But what I cannot have is one constraint that contains all of those. It simply doesn't make sense. As I go to create my constraints, I need to make sure that if I am describing this time in minutes, so if I look, as is pointed out in the question, manual work time takes 20 minutes for the modern lamp and 30 minutes for the classic lamp. But now when I create the right-hand side of that equation, I need to make sure, because this was expressed in minutes, that right-hand side better be expressed in minutes. So I was originally given that I have 100 hours of manual time per month available. I cannot have minutes, hours. I need to convert that into minutes. So 100 hours times 60 minutes per hour, we get a total of 6,000 minutes. There would have been no issue. If I had preferred, I could have just as likely expressed this in hours. So 20 minutes is a third of an hour. Okay, or I could express it in decimal form. I could add 1/3 m. 30 minutes is half an hour. So 1/3 m plus 1/2 c is equal to 100. As long as I'm consistent within this constraint, everything is okay. Again, constraint by constraint, I need to make sure that within that constraint, I'm consistent. And again, here I've converted everything into minutes. So in terms of machine time, the modern lamp takes 20 minutes. The classic model takes 10 minutes. And I have converted 80 hours per month into minutes by multiplying by 60. But had I wanted, once again, I could have expressed this in hours as long as I was consistent for the entire constraint. So this could have just as likely been 1/3 m plus 1/6 c is less than or equal to 80. And then we have one final constraint that deals with capacity. The maximum that this company can make is 500 lamps per month. So the total number of lamps in M plus the total number of lamps in C has to be less than or equal to 500. Remember, capacity, I cannot make more than that. That is the absolute maximum we can make. And then never forgetting our non-negativity constraint, neither M nor C can be less than 0. And now we have our mathematical model, and we can go and graph this linear program. So starting our linear program by graphing each of our constraints individually, disregarding the inequality. And had I kept this in hours, we would have ended up with the exact same line here. These would have been in a different unit of scale, these numbers, 20, 30, and 60. But because they're all relative to each other, when I go to graph this line, it would be the exact same line. So graphing constraint 1, followed by constraint 2, and now constraint 3. Once we graph all those lines, now we're going to go and shade the appropriate side, depending on whether it's a greater than or less than constraint. Constraint 1 was a less than or equal to. We will shade towards the origin. Constraint 2 is less than or equal to. And constraint 3 is less than or equal to as well. When we started this series of videos, the first special case we saw was infeasibility, where we didn't have a feasible region. Well, that's not the case here. I have this region here, which is shaded by constraint 1, constraint 2, and constraint 3. This little region here is shaded by all of those, so infeasibility is not an issue. Our second special case was unboundedness, where the feasible region was created, but it was infinitely large. Well, that's not the case here. I can see that this is completely bounded by our non-negativity constraint on this side, our non-negativity constraint on this side, constraint 1 here, and constraint 2 here. So we're okay with infeasibility, we're okay with unboundedness. The special case that we have here is that we have something called redundancy. Redundancy occurs when we have a constraint that makes absolutely no impact on the feasible region. So here I can see that constraint 3 is in no way part of this feasible region. So this constraint is considered redundant because whether it exists or it does not exist, it doesn't change anything at all in my solution of this problem. When we dealt with infeasibility or unboundedness, we ended up with a problem that was unsolvable. We could not go any further. Redundancy does not lead to that same situation. When we have redundancy, we can now go and solve this problem. I can now go and graph my objective function and then find out which of these 3 points, and it will be these 3 points because the origin is never going to be the optimal solution when we're dealing with a maximum profit example. So I definitely know that either this point, or this point will get me my optimal solution. So this is solvable. It's just we have stuff in the model that we don't need. So in the real world, these problems can get really, really complex with many, like hundreds of different arguments in them. When we find a redundant constraint, it is often best just to remove that constraint so that it doesn't unnecessarily add to the complexity of the question or the computational power that is needed to solve for it. Whether we remove this constraint or not will not affect our answer, but ideally what we would do is to remove this constraint since it has no impact on the question at this point. As always, please email me with any questions that you have about any of the material. Thank you.